Hi guys, this is your crazy astrophysics guy again. Wanted to say, hey, this is my first day of teaching on YouTube, so I would like to say hi to everybody who's following me, and thank you for everybody who's following me. It's been a wild ride so far, and even though this is my first day of teaching, yes, I am outdoors. This is my outside zen, pretty much, is what I would call it. It's Friday, October 2nd, around 2:45 p.m. And this is where I usually go. My lab, I'm actually moving into a different one, so I do have my whiteboards there, so I got to unpack them too, so it's going to be interesting to get that all done and see what's going on with that. So yeah, it is what it is, I guess. But first and foremost, I want to dedicate this episode to two of my closest mentors that I ever had in my life. My dad, John Clarence Cover. I know I talked about him probably a little bit before. He was actually a missile test inspector for NASA. He worked at Cape Canaveral way back in the day. He actually inspected the Atlas rockets from the Mercury and Gemini program, and that's where I get my love of NASA and everything from him too. I'm also dedicating this to my cousin, John Richard Cover, the astrophysicist. He was working at Kit Peak. Way back in 1982. It was in March of 1982. We visited family out in Tucson, Arizona, and I remember stepping out of the car and looking at the big telescope, and I'm like, this is exactly what I want to do with my life. This is exactly what I want to be when I grow up. So he got me situated on a program, and I followed that program until I graduated. So it's been a wild ride. Been a really, really wild ride. Like I say, it's been 43 years. I'm doing this on my own. Actually, I got a couple professors. I got a couple of professors. I can't even talk. They're all supporting me on this, and I thank them. I thank you guys for supporting me. Just, even though you can subscribe to this and you like this, doesn't mean you necessarily have to agree with it. I mean, most of this is factual, so I'm not getting into my own work here, but pretty soon I might be. Like I say, these are all copywritten, and why not? So I wanted to start off with a little bit about iterative functions, because I always say live 5 iterations above the norm. That's actually a family that comes from my dad. So he always, every day before I went to school, he's always like, live 5 iterations above the norm. And I'll actually tell you what that is right now. If you see this whiteboard, and these are not the only whiteboards I have, by the way. You can see where all these different functions, these are what we call functions: f of x, g of x, h of x. That's not a smiley face. That's just dedicating that's I. I with the 2 dots is regular I. Now, just I would equal the square root of -1, which is not exactly what I wanted to accomplish there, but that's what I with the 2 dots is. It's just I to the x, which is a function. Then you have j to the x, and then they go backwards just because that's how they do it in quantum physics. A to the x, b to the x, and c to the x, c to the x. Just knowing that all of these can be in an iterative process or an iterative function, all of those can be the same function. They don't necessarily have to be, but in an iterative process, it kind of is. But what I wanted to make sure of is I wanted to make sure that astrophysically we are taking it to the real level here. So that in that case, you actually come up with this, if you can see it. So we have f of g of h of I of x. Now that's 4 iterations. F of g of h of I to the x. So that's iterating 4 iterative functions right there. Now you see that plus j to the x with the asterisk above the x? That indicates a complex conjugate, which means it's that one equation after the 4th iteration. At the 5th iteration, it starts to go both ways. It's both negative and positive at the same time. Now you see that at the end, the plus c? Well, that's where you add the next iterations at, because it changes the equation. At that equation, you'll have a different set of figures, like a of the b of the c to the d, and then it comes back all over again. So in astrophysics, when we say that it's always been 5 iterations, it actually is, because you have, and this is where I'm going to go into current events, because I do get mad at some people, at some scientists. They're actually wanting to say that astro should not, because a star doesn't burn hydrogen, it shouldn't be called a star. So in astrophysics, anything that fuses together should be called stars. They're out there, they're burning some form of derivative of hydrogen. So in a sense, and right now astrophysics really can't pinpoint how many different complex systems are working at the same time in a star. Like take our sun for existence. For instance, for existence. Well, that too. It exists, so I guess it does. But in as much, I want you to think about how many different complex systems, different complex systems are in us. I mean, we use a Krebs cycle, but that's breaking down glucose. It's not exactly fusing elements together. However, we do have different DNA sequences. I'm talking genetically. So there is that, and that's several hundred complex analysis all in one. I mean, take a look at mitochondrial RNA, for God's sakes. I mean, how many different complex systems are in mitochondrial DNA? And actually, you can see the exact same equations with genetics as you do with astrophysics. I mean, it's crazy. After the 4th iteration, you always have a complex conjugate on the 5th iteration. That's gone all the way back to when Feigenbaum had his constant, because it was, they always. Okay, I'm going to start here. In 1976, Benoit Mandelbrot came out with his iterative processes, and it actually came out to what they call the Mandelbrot set. It revolutionized everything, because they actually found out that, yes, nature does have a pattern. There are different sequences and series to different forms of sets of equations. Like I said, all these functions that I showed you before, each individual functions could be the same function, or they could be different functions that actually iterate in themselves. So the sun itself could have hundreds of billions of complex systems. We really will probably never know how many complex systems are in a star, because like I say, that formula that I showed you before, the 4 iterations of one, that's only of one complex system. And you're talking about infinite number of complex systems within that star. So, like I say, at the complex conjugate, which is the 5th iteration, you have a spinoff because you have abelian and non-abelian, which I'll get to that in a later episode. You have an abelian set of equations, and you have a non-abelian subgroup. And in those subgroups, that's where all of the fusion, and I'll actually give the chemical equations to this next time because I don't have a whole lot of time today. I'm not working today, but that's why I'm out in the park and kind of enjoying the day itself. But at another time, I will get back to the chemical equations that these actually persist of. Because you have oxidizing agents, you have reduction agents, you have all kinds of stuff going on at the same time. And that's usually in your 5th iteration. If it wasn't for the 5th iteration, we wouldn't be here. Because it takes a lot, and I mean a lot of time, if you don't have the different, what do I want to say here? If it wasn't for supernovas, supermassive supernovas, a huge number of them, we wouldn't have the amino acids it would take to create the DNA sequences that we actually need to survive. It literally does, we actually do come from water. So H2O is where it's all at. And actually, I proved this 6 years ago from the High-Fay experiment. They, when they're fusing elements in a sun environment, I want to say sun environment because they are fusing hydrogen, deuterium, which is 2 hydrogen. You have 2 protons of hydrogen. You can still have, 3 protons of hydrogen would be tritium. But yeah, ultimately the High-Fay experiment, which I'm talking about right now, they only used 1% of my design for that. They didn't put enough air pressure valves in there. That's why it got so hot. Another thing I'm going to say on here, you only guarantee what you're engineered for. So when I designed this, and I started this way back, oh my God, I was at Logansport High School when I when I first started the design for this. I was a sophomore in high school, and I still remember trying to figure out what kind of material I would have to have for my outer shell to actually keep this from exploding and imploding and all kinds of stuff. And another thing about me, I don't go off willy-nilly and I'd say, okay, I'm going to do an experiment tomorrow. There's a lot of safety issues that I like to put in. There's a lot of different sets of, I'm Diogenes Laertius of goniology, let's face it. I'm looking at every aspect. Is it safe astrophysically? Is it safe chemically? Is it safe environmentally? There's a lot that goes into this. Like I say, I started way back when I was a sophomore in high school going, okay, what kind of material do we need? What kind of material does this have? It's still, and I'm in redesign on that project too. I need to find a material like Rayethon that stretches. That way we have enough pressure valve in it without having to melt it at the sun's temperature. I want to keep it a main sequence star. That's the whole That's the whole issue. That's the issue that Hi-Fi didn't have. They started at helium-4. When you start fusing with helium-4, I'll tell you this right now. When you start fusing with helium-4, you get a supermassive red giant. Now, can we contain a supermassive red giant? Not right now. I mean, we're having trouble containing and constraining a main sequence star, and that's only by using deuterium and tritium. Actually, deuterium is probably the best to actually start fusing, because at that fourth iteration, when you're fusing materials together, that fifth iteration, you better have something that will make that magnetic confinement time be spot on. Now, when I say magnetic confinement time, I mean to go from unstable to stable. Now, to stabilize this thing, you would have to have the right pressure, which I had everything figured out. I had it all on paper. I've still got it on paper. It's in my files. My files are packed away, of course. But eventually I'll get them out, and we'll see where that goes with the redesign, of course. But yeah, I had everything figured out. I had everything piled, and I was actually going from company to company in the United States, wanting this to actually to become something. You ought to see the looks on people that, you go to their company to talk about your product, and they say, well, what is this? And then you say, well, this is an infinite number of hydrogen bomb explosions centered around a central core. And everybody's like, and you try to explain what kind of materials you would have to actually contain that, which Hi-Fi did a decent job of doing. They actually see that project somewhat of a failure, but I see it as a very big success, because they did get 102 seconds worth of sustainable fusion. They didn't build a big enough capacitor to hold all the energy, so most of the energy went into the atmosphere. And that was they could have done that a lot better. They could have probably built a better capacitor for the energy that actually they were storing. So that could have been a lot. It would have been a different outcome, let's say, because things get out of hand sometimes. But 102 seconds worth of sustainable fusion is awesome. You could run Shanghai for 6 months off of that energy. Yeah, and you're telling me. I'm wanting to actually, what my experiment on this fusion generator, and I started it, like I said, way back when I was a sophomore in high school, and I actually marketed it as the gravitational fusion, which it has what it has. I mean, it had the right density. I had the right material for the right pressure. Had even the flow from the needle going up from the bottom into the ignition was spot on. Had the right volume. I had the right pressure. Had the right exact elements with the right amount of fusionable material. Now, you have to have fusionable material to do that too, because if you don't, you're not going to have that spark. You're not going to have that. It's like lighting charcoal with a pressure cooker. It's not going to work. So I was glad for them that it did work. I know most of you have already seen it, most of you watching right now have seen this. I did get accommodation. I do have a star named after me for that. I still thank everybody for doing that. They didn't have to. It's just one of them things, I guess. But in as much, I know I'm rambling on here, and I'm sorry for that. Sometimes I do get off track. I'm human. That's what we do. But yeah, that's why I always say live 5 iterations above the norm, because that's what we do every day. And I'll talk to you about the chemical equations next time. I'll talk about hydrocarbons next time, because that's the 5-carbon chain hydrocarbons. I can talk to you about chemistry all day. I've got chemistry sets in my lab somewhere. I've got all kinds of stuff. So, yeah. It's been, like I say, it's been a wild ride. This is my first time teaching. I hope everything goes all right. I hope you could read everything. You may have to write it backwards. I didn't really realize that until I looked at it, and I'm like, oh, I hope everything's the right side. Sometimes you don't really think of that when you're teaching. By the way, there was a question. Yes, this is a lot different than teaching in a classroom, because this is live. Well, it's live for me. And I will be reading comments. Please leave comments, questions, anything like that. I implore you to do so. And there is, like I say, there is no stupid question. There's, and if I don't know the answer, I know the people who are backing me who actually do have answers. So, like I say, always live 5 iterations above the norm. So, I guess I will see you guys later. So, have a great day. I know it's pretty nice here, but I will, until next time, have a great one. Thank you. Bye.